All right, so this is the Unit 2 text. It looks a lot like, in the beginning at least, the Unit 1 text. And it covers everything that we're going to cover in Unit 2, in class or with distance learning or virtual learning, okay? All the stuff you learned in Unit 1, you still have to be able to do in Unit 2. We won't do a lot of math problems. In fact, I'm not sure we'll do any math problems exactly in Unit 2, where you have to do the rounding off with addition and subtraction, multiplication and division. But you will have to do that in future units, so you need to have a good understanding of significant digits. We are going to start talking about atomic structure in this unit, okay? And we're also going to talk about the periodic table. So you have a periodic table. You have a set of test references I gave out to you on the first day. I can probably post those in the Unit 2 section where I'm going to put the extra credit, I guess, with the text, so that you can look at that. You've got the same references on white paper that we will also use in on the test. Only when you take the test, the references are on yellow paper, and you only use my references. You don't use your personal references, because you can write notes on your personal references. So my references are clean when you start with them, and that way, it doesn't provide a way for you to cheat by doing that, okay? So I'm going to refer to this, but I'm also going to go back and show you on my document camera how to do some of these things. So, and while we're doing it, we might also help you with some of the annotations, so that at least for the Unit 2, because this is one you could edit. I've given you your copy. It's got your name on it. You can actually do annotations. So headings and subheadings, highlight those. I'm not going to do everything. I'm just going to start you off. Let's see. Whoop. If it'll work with me, here we go. Here we are. Come on. And we're going to highlight that in yellow. Okay, so headings and subheadings, you want to highlight those in yellow. Okay, and then when we get to these section headings, the questions here are the kind of questions that you should be able to answer when you finish studying this unit or this section of the unit. And the questions are: what are the representative elements? What are groups or families of elements? What elements make up the alkali metals, and how are they different from group 1A elements? What elements make up the alkaline earth metals? What elements make up the halogens, and what elements make up the noble gases? So as you go through here, you should be able to figure that out and answer those questions. And so if you're going to write your learning objective, you would go through here and look at all these headings. One of the reasons for highlighting headings is to help you focus on the fact that you're going through there and looking at those headings, okay? And then look at images, okay? So here, this image tells you where the representative elements are located on the periodic table. And so you want to look at the images. And that's all that really shows here, okay? And then go to the next section. In fact, I probably need to put a page turn right there, but it didn't show up that way. So all these questions are answered in just this short section right here. Okay, so what we want to do is to get out your copy of the periodic table. If you have your copy of the periodic table, let's pull that out and look on with me. All right, so I have my copy of the periodic table here. All right, and so as we go along and look at these things, we can refer to what's on this periodic table, okay? And it would be good if you had those. Actually, I'm not realizing that you guys were not going to be ready to ask questions about Unit 1. And by the way, anybody joining late, the only reason we're going over Unit 2 right now is because I gave everybody the opportunity to ask questions about Unit 1, and nobody did. So at some point, if you guys are going to start asking questions about Unit 1, I need to know, and I can stop teaching Unit 2 and go back to Unit 1. If I need to answer any questions to help you prepare for the test. All right, so representative elements. Representative elements are the elements that are in the, let me put this on this screen here, are the elements in these first two columns. Okay, now this is where you need to take notes. I don't tell you all the time to take notes on things. I mean, you got to get in the habit. You really need to get in the habit of taking notes when I'm telling you about things, because if you don't take notes and you don't remember it, and we get to the test day and, well, I don't remember that. Well, I taught you that. You need to take notes and ask questions, okay? So the representative elements are the elements in the first two columns of the periodic table and the last 6 columns of the periodic table. All these elements here and here make up the representative elements. And the reason those are called representative elements is because they're the easiest to see patterns on the periodic table. The reason the periodic table is laid out the way it's laid out is because it tells you, you can look at the periodic table and figure out a lot of the properties and behaviors and structures just by where it is on here. The reason the periodic table is put together this way is because elements in this column have certain chemical properties in common. These in this column have different chemical properties in common. These in this column have different chemical properties in common. And when you understand why, then you start to understand that these all have a similar structure in some part of the atomic, in particular in the what am I trying to say here? Oh, the electron cloud. And so these are the easiest ones to figure out what's going on, and these are a little more complex. And this section here, right in here, these are called the transition elements, okay? Now, this section down at the bottom is actually part of the transition elements. If we were to take the periodic table and cut it with a pair of scissors right here and slide all this over, this part would stick right there. And if you notice lanthanum here, it's element number 57. I'm pointing to lanthanum here so you can look on your periodic table. Lanthanum is element 57. Well, 58 is right here. And so this row goes to 71, and then 72 is right here. So this stuff really belongs in that section, but if we put this in there, we'd have to shrink this thing down, and it'd be even harder to read. And, you know, some of the writing on here is already kind of small. So that's the reason the periodic table is laid out the way it's laid out. So the representative elements are here, and these are transition elements. And this section down here is called, or these are called the inner transition elements, I-N-N-E-R, inner transition elements, okay? So let's go back now and look at the next question on here. And if I'm writing a learning objective, this is all about where the periodic table is laid out and where some of the major categories are. So I would write something like this. What I expect to learn. Okay, so that might be my learning objective, okay? So that if I'm studying this, then when I'm getting ready to do the test, I know where to find this stuff, and it helps me to keep in mind in categories. You know, if you create files in your computer, it helps you to find these categories of documents and images and whatever you saved on your computer so you can make your own files. This is kind of the same thing. We're creating a way for you to mentally have files of where you will learn these things. It helps you to remember them when it comes time for the test. You don't just have this subject and the next subject and another subject after that, and it all kind of runs together. You have categories and then subcategories to help you organize mentally where the information is for your being able to be successful on the test. Okay? All right, alkali metals, and that's the next subject. All right? Oh, wrong thing. Why is there my camera? Okay. The alkali metals are the metals that are in this first column. And I put it that way because hydrogen at the top is not really considered to be a metal. Now, theoretically, it should behave like a metal if the pressure is great enough, and the temperature too, I guess. But you have to have pressure like the kind of pressure you'd have on the planet Jupiter near its rocky core. So Jupiter is called a gas giant. Most of Jupiter, at least in terms of its size, is made up of gases. And down near the center is by comparison, it's kind of a small core, and the pressure on there is just immense. Nothing like you can imagine. You'd have to put hydrogen under huge amounts of pressure for it to behave like a metal. And until we get to that, hydrogen behaves like a gas. So the alkali metals are starting at lithium going down to francium and don't include hydrogen. So one of the questions up there near the learning objective was how are the alkali metals different from the group 1 elements? Well, that's because hydrogen is not one of the alkali metals. Okay. All right, so then the next question is, what elements make up the alkaline earth metals? So the alkaline earth metals are this second column right here. Okay, alkaline earth metals, second column of the periodic table. Okay, these all have similar chemical properties. Even hydrogen has some similar chemical properties to these elements. We'll get into more probably in the next unit than this one. And these have different chemical properties. By chemical properties, I mean, how do they react with other chemicals, with other elements, for example, or other chemicals in some cases. So the next question is, what elements make up the halogens? All right. This column right here, next to last column on the right, those are the halogens, okay? And I'm pretty sure the next question is where the what are the noble gases? So the noble gases then are the last column over here. One thing you need to know about the noble gases is this. For the most part, and we're going to treat them this way, these do not chemically react with anything. So they're considered to be stable, okay? Now, you actually can get some of the larger noble gases down here, krypton and xenon, to react with other elements. There's a really interesting gas called xenon tetrafluoride that is a really heavy, dense gas, and it has some behaviors that are really interesting. You may have seen examples of people breathing in helium and then talking, and it sounds like, cartoonish or something. The pitch of the voice goes way up when you do that. With xenon tetrafluoride, if you breathe in that and talk, your voice gets really low. And we'll talk about why that is more when we get to Unit 7. Okay? So one of the activities I'm going to have in this unit is I'm going to give you outlines of the periodic table, and you are expected to take one of those outlines of the periodic table and outline where these alkali metals are and label them. And outline then where these alkaline earth metals are and label them, and outline where these halogens are located and label them, and outline where these noble gases are and label them, okay? This column here, starting with oxygen, actually has a special name like halogens. They're called the chalcogens, but I don't expect you to know that. For these 1, 2, 3, 4 columns here, you just need to know that we're going to call this column by the element at the top, okay? So this would be the oxygen family or oxygen group, the nitrogen family or a nitrogen group, okay? They all have special names. We're just not going to learn those special names, just those alkali metals, alkaline earth metals, noble gases, and halogens, and then transition elements and intertransition elements, at least at this point. So when you label that periodic table I'm going to give you, then you need to make sure that you take care of that. You know where those are, okay? All right, let's go to, I think that covers everything in this section. Yep, all right. So now we're going to go down the next section. What is a quantum of energy? Now, we don't really teach quantum numbers anymore, and I need to take some of these out. Unfortunately, it's already in here, but I'm going to tell you what a quantum of energy is, because that really is important for the way that we understand the structure of the atom, particularly the electron cloud. Energy we think of as being, like if you go to your stove and you turn the knob, the heat goes up. And if it really did go up in that smooth sort of way, that would be an analog change. But technically, the way that energy works is you don't have smooth changes. The changes are so tiny you can't tell they're graduated, but they are. And so those energy actually comes in what are called quanta. And the way the atom structure is made up, the way that the electron cloud in particular is made up, where you have these different levels where the electrons are located, that's all based on quantum energy, how much energy that electron has. So every electron, by virtue of its where it is in the atom and how fast it's moving and all those things, give it a certain amount of energy, and that amount of energy it has is defined as a quanta. So the first quantum is really big, and the second one's smaller, and those after that get smaller and smaller. So we're going to go down to this next question here. What are ground state electrons? Ground state electrons can be defined as the electrons in the lowest possible energy state. So we talked about quantums of energy, and what do quantum numbers tell you about electrons? Well, since we define the energy of an electron by quantum energy, then the ground state electrons have the lowest quantum energy, okay? Now that doesn't mean all electrons can have that same energy, because you can't fit them all in the same level of the atom. You have to go, you can only put 2 electrons in the lowest level, and then you can put 8 electrons in the next primary level. There are sublevels within that, and then up to 18 electrons in the next one. And so those electrons can have similar energies, but they can't have, all the electrons in an atom can't have the same amount of energy. Well, what a primary electron energy level look like if we could see one? Well, you can't actually see one. We call the, they call it the electron cloud, because we have an idea of where they are mathematically and statistically and in terms of physics, how people have done the research. But if we could see the way the electron cloud is made up, the primary energy levels would look like circles or spheres, really. So you have the nucleus in the center. Let me just draw this out for you. Okay, we have the nucleus in the center, okay? And then you have a the first primary energy level would look like a sphere around that. Now we draw it as a circle because a piece of paper is only 2-dimensional. In order for it to be three-dimensional, I'd have to have things coming out toward you, and I can't do that on paper, and we're used to that. But beginning in this unit, you've got to start thinking in terms of three dimensions. It's not going to help you if you can't at least imagine. I sometimes call it running the movie in your head. Like you in your head, you remember, oh, this has got to be three-dimensional. So we got the horizontal dimension and the vertical dimension, and then the one that comes out toward you and back behind the paper. Okay, so this is supposed to be a sphere. You got to think in terms of that. The second primary energy level would be a second sphere surrounding that. Okay, the third primary energy level would be a sphere surrounding that, and so forth. And they keep getting larger and larger and larger. Okay, up to at least right now, and we're only going to talk about the structure of the atom as it applies to the ground state. Okay, so we're only going to deal with as many rows in the periodic table as we have, and we have one rows that go side to side. They're horizontal. 1, 2, 3, 4, 5, 6, 7. We're only going to deal with 7 primary energy levels, but we are also going to deal with sublevels within those. Okay, so that's one of the things we're going to talk about in this unit. What are the sublevels, and for that matter, within the sublevels, what are the orbitals within that? Okay, we're not going to deal with quantum numbers per se. We are going to deal with letters that represent much the same thing. There are actual quantum numbers. Every electron has a kind of address. It's like you have an address. You have a number for your house. You have a street name. You have a city. You have a state. You have and a zip code actually tells the letter carrier what area within a city you live in. It doesn't tell you everything. It doesn't tell the zip code unless you use the 5-digit extension. It doesn't tell you what your actual house number is or what really close to where your house is. But it's kind of the same thing. We're not going to deal with those actual quantum numbers. You probably will have to learn about those in college. But we're going to deal with sub-level letters that will tell us about those, largely the same information. The difference is the sublevels don't really give you, the sublevels and orbitals don't really give you an address so much. But we're going to talk about what that, where those electrons are and what their spin is. That would be have to do with how the orbitals work. And so that those sublevels, those levels, sublevels, spin, orbitals, and spin are where you get the 4 quantum numbers for every electron. We don't learn what those actually are. So when I started modifying this copy of your text for you, I did not realize that those questions still reflected some of the old information I have taken out of the actual text. Okay. But it describes what quantum numbers are here, all right? Now, and this seems to be off the screen a bit, all right? So what I want to do is I want to go here, and I want to hit return. I want to move this image down so I can see it. Okay. So this is then an illustration that kind of shows you the same sort of thing. It shows you what we're talking about, all right? When Niels Bohr, B-O-H-R, Niels Bohr, first proposed what the structure of the atom was in terms of those quantum levels, those energy levels for electrons, he imagined that it was this kind of concentric sphere arrangement I'm talking about in my illustration. Now, my illustration here is two-dimensional. You're just seeing the circles, but the actual shape of it, I've got an illustration of here in your text, okay? So you got a first primary level here, and a second primary level here, and a third here, fourth here. I'm showing 5 on the periodic table. We have enough elements to identify, 7 different primary levels, okay? All right, then. What symbol is used to designate the first quantum number? Since we don't actually deal with quantum numbers, the first quantum number is indicating what these primary levels are. Okay, so we would call this level 1. And when we do orbital notation and electron configurations, that will be identified as those electrons there will be identified as being in level 1. And this would be level 2. And this would be level 3. Okay? So the next question is second quantum number. The second quantum number identifies what sublevels electrons exist in. Now, this illustration doesn't show you the sublevels. That gets more complex. And it would be too complex to show you the whole structure with levels and sublevels and orbitals for the whole thing. You've got to kind of take one at a time to understand. Okay? Then this is only dealing with those, the second quantum number, okay? And we're going to talk about orbital notation and electron configurations, because orbital notation and electron configurations kind of give you, raise your hand or give me a thumbs up if you've ever done an inventory in a store. Nobody's ever done an inventory in a store? Okay. In a store, in a place of business, you do an inventory to count everything in there. In particular, you count everything that's for sale in there. Now, that isn't always the case, but most of the time that's what you're doing when you're doing an inventory. And so your spreadsheet or your worksheet will show that you have so many widgets, okay? And it might say you have so many widgets on the floor and so many widgets in storage. It depends on how it's set up for that particular business. Orbital notation and electron configurations are kind of like that for electrons. They tell you where the electron is located. Orbital notation tells you more information about the electron. Electron configurations tell you a little less information, but you can infer the same information once you understand orbital notation. Okay? All right. So then this goes through kind of all those things. I need to weed some of that out, but that's primarily the stuff that you need to know about in this section here, okay? Then in the next section, orbital shapes and names. So within these primary levels here, you have orbitals. So this is the primary level, and within that you have orbitals and sublevels. So the orbitals, there's different kinds of orbitals in each sublevel, okay? So in this first primary level, there is only an S sublevel. In the first primary level, there's only an S sublevel, okay? And it has this spherical shape, okay? So in all these primary levels, they all have S sublevels. And the S sublevel always has that spherical shape. That S sublevel is also the same as the orbital that you have in that sublevel. So the first primary level has a spherical shape. The sublevel S is synonymous. It's the same thing as its spherical shape. And the orbital, the only orbital that has that first orbital, the only orbital that the S sublevel has is spherical. So this primary level, orbital, and sublevel are all the same shape. It's the same thing. We get to the second level, then we start to split it out. There is an S sublevel, which again is that spherical shape, has the same shape as the primary level. The only orbital that an S sublevel has that same shape. But within this second level, we also have sublevels, and those orbitals have a different shape. Okay, we're going to get into that. Let me take a look over here real quick and make sure that I'm giving you in order for the text as I'm following along in the text, trying to help you with that. And if you're reading the text, if you have it up on your screen, I would suggest, you can start doing, since we're going over it in order, you could do some of those annotations as we go along here to try and help earn extra credit on your next test. So while we talk about it, you can do that if we're talking about it, okay? All right. So within this second primary level, then, we have an S sublevel. We also have a P sublevel. So let's illustrate that on a separate sheet of paper. If you're taking notes, as you should, then I'm going to just illustrate the second primary level here, okay? So we'll make it bigger so you can see. That's kind of oblong, but this is the second primary level that we're talking about here. So that first primary level is inside of that, all right? In the second primary level, we have two kinds of orbitals and two sublevels. Each sublevel has a different kind of orbital. So the first orbital we have is that s orbital, which is synonymous, the same size and shape, is the same thing as that primary level. The second sublevel, so we have an s sublevel, and I'm going to label this here as sublevel. I'm putting it over here kind of in the corner because I know what's coming next. Maybe you might want to wait to fill that in. And then we're going to have a p sublevel. Now we can't designate what that p sublevel looks like as such. All we can do is designate what the p orbitals look like, because the second primary level has to do with the orbitals themselves. Okay, it's the fact the orbitals exist in there. Now the orbitals we usually represent, we usually illustrate those as being double balloon shapes. So remember those on your, if you look at your tests, if you look at your syllabus, there's certain supplies you're supposed to have. And those supplies include balloons. Well, we're going to make models of these balloons. So you need to go ahead and get your balloons. So after the test we're going to do on Monday and Tuesday, the next in-class day, I want to start you with making balloon models. So make sure you have your round balloons, okay? So, in fact, I'll just color code this for you. We'll call the p sublevel is going to be made up of 3 orbitals. So I'm going to have one orbital that looks like this. So this double balloon shape is a p orbital, all right? So I hope you're taking notes and drawing these drawings, because this is going to be necessary, okay? You know, if you don't have a drawing of this, it's not going to help you in the long run. I left this dotted here because I'm going to draw something over it in a minute. So really this is not a broken line, but it's just kind of showing how something else is behind it when I get there, okay? All right, then the p sublevel actually has 3 different p orbitals. I'm going to put 3 here in parentheses. Okay, to remind you that's the case. So let's see here. Let's make the next one. I can find it. There it is. We ought to have another p orbital we're going to make. We're going to do it 90 degrees to this. Same thing here. I've got a dotted line because I'm drawing something in front of it here in just a minute. So this is a p orbital. Again, this is the same p orbital. It's just in 2 parts. Okay. These 2 parts here are called antinodes. A-N-T-I-N-O-D-E-S. Antinodes. The node for this orbital is actually right here where the nucleus is, and the antinode is here. Well, that corresponds to what you may have learned about waves. This is actually a wave pattern. So you may have learned in another science class about sine waves. They look like this. You remember learning about that? Anybody? Hands, thumbs up? Nobody? Okay, some people remember that. Okay. So the whole wave goes from here to here, or from here to here. As long as you start at any place on the wave and go to the next wave that looks exactly the same point on that wave, that's the whole wave, okay? These locations on the wave, these are called the antinodes, okay? And then the node, oh, I misspelled that, node is located right there. Of course, I don't have my white out in front of me. I was going to erase that, but anyway. So even though it might seem kind of strange to you because you've never seen that before, this is actually a wave pattern, okay? So the antinodes are here and the nodes here. Now, you don't have to know that, but when we talk about what these are, and I tell you that's an antinode, I just kind of want you to know what I'm talking about, that means kind of the same thing, okay? All right, then we have one more p orbital within that p sublevel. And the difficulty here is this orbital needs to come out toward you, okay? And it needs to go back. The other part of this, you got two parts here. It needs to go back behind the paper. How in the world do we draw that on a piece of paper? Anybody take an art? If you take an art, raise your hand and give me a thumbs up or something, okay? So you, Guillermo, you know what perspective means, right? Okay, so we're going to like just turn, it's kind of like we're going to take this orbital that's going back and forth, back behind the paper and out in front of the paper. We're going to tilt it just a little bit so we can kind of see perspectively at least what this orbital looks like. It's kind of strange because we aren't turning these orbitals too, but we're going to tilt this one a little bit so you can kind of see it, okay? It's just kind of simplifying the illustrations, even though it's kind of not really completely perfectly laid out. So I'm going to do it by drawing this one out in front of it like this. So this is just the same shape as all these other antinodes. We're just trying to show that it's coming out toward you, okay? And the other part then is going back behind it. So in perspective, we're going to make that smaller, okay? So this is also a p orbital. I'm going to write p orbital over here. And I'm going to draw an arrow to it, okay? All right, so you know that's what that is. All right, so that's the shape of a p sublevel. The way that the orbitals are laid out makes up the shape of a p orbital. And so that's like two balloons and two balloons and two balloons. And we're going to make a model of that in class, okay? And then to get you started, in the next unit, we're going to make models also of molecules. And for those, you're going to have long balloons. But just for now, in this unit, by your next, well, the next in-class day is a test day. The day after that, the next in-class day after that, we'll start with giving you the copy, or I may actually, let me see. Yeah, with this distance learning thing, I'm trying to figure out what I'm going to do in class and what I'm not. I may give you a copy of those periodic tables I talked about earlier to take home and work on those as a distance learning day on the day of the test. And then we'll do the balloon, start the balloon models on the first in-class day. And then when we get to the next unit and we're doing balloon models of molecules, we'll start in class and you'll be doing a lot of the work at home, and I'll have videos for that. All right, let's see where we are now in the text. Okay, what's the shape of an s orbital? What's the shape of a p orbital? How are the s orbitals and p orbitals arranged? Well, there you go. We've done that. All right, we've got all that set up here for you. Okay, you've seen all that here. All right, maybe it's a little bit. Okay. Now, in your text, this illustration actually shows a little more of what the p orbitals really are supposed to look like. And that's kind of strange. We don't think about it that way. We don't illustrate it that way. And in most textbooks, you don't even see it drawn that way. But this actually shows what they are supposed to look like. Let me try to explain that. So if you remember when we were talking about this, I'll see if I can find a different color to illustrate this for you. Remember that first s orbital is right in here. I don't know if I want to draw that or not. It might make it too complex. That first s orbital is inside of this. Well, these p orbitals really aren't part of this lower level at all. So the only part of the p orbital that really exists is that which is outside the s orbital, this much of it, okay? And this much of it here. So this p orbital really doesn't even exist in this region here. But because that's hard for people to imagine and understand, we usually illustrate that as a double balloon shape, okay? I know that seems kind of strange, and it is. We're talking about strange looking things and strange behaviors at the quantum level. In fact, one of the behaviors that Einstein described when he was talking about the way the electrons or any particles, these kind of subatomic particles, the way they behave, some of those behaviors he called spooky action at a distance. Einstein actually used the term spooky to describe this sort of behavior. Okay? I think that's kind of funny. Apparently y'all don't think it's funny. That's okay. All right. It's chemistry humor, I guess. All right. Physics humor, maybe. And so those p orbitals then are arranged like this. So you can see I don't have a double balloon going from here to here. Okay. What I have are just the top of the balloon here and the top of the balloon here. And it's outside where that s orbital would be located. Okay. And here I've got it arranged so that this s orbital that we had in blue on my illustration is actually just looks like a circle here, but it only shows the part that's sticking out toward you. So this is a correct perspective if it's turned, basically in this orientation for you, okay? And so it's pointing out here that you also have that lower primary energy level inside of all of this. And that's why the p orbital has this kind of scooped out section right here. It's not really shaped properly because I wanted to kind of emphasize the fact that it kind of cups over that lower primary level. Okay. All right, then now what I've done is to take this illustration that I did on paper and turn it a little bit more so the perspective is more correct. Maybe this might make sense to you, Guillermo, since you've taken art. So that now I've got all the orbitals in a correct orientation for perspective. But again, it looks kind of strange here. Each p orbital looks just like this. But if you turn it in a certain direction, it kind of looks like this to you, this part and this part. And I've labeled these, okay? I've called this the x-axis, and this here and here I'm calling the z-axis, and here I'm calling the y-axis. So you're familiar with x and y on these Cartesian planes for the graphs we do. But there are 3 dimensions, and so there's a third axis that doesn't exist on a Cartesian plane. There's a third axis called the z-axis, which is the one that comes out toward you and goes back behind. Okay, and so this is trying to kind of give you an idea of what that might look like. And so in this case, I put some places for you to write review questions into your text. Okay. All right. And so here I've defined for you what the Pauli exclusion principle is. Okay. Let's go back to our list of highlights up here. How are we supposed to highlight definitions? Well, it's right here. You highlight the definitions in blue. Let's go back down here and look at that. So since this is a definition, I want to go ahead and highlight that in blue. I'm going to highlight it with my cursor on my computer, my mouse button. And then I'm going to click up here and find a blue color, and now I've highlighted it in blue. Okay. If you don't like that dark color because it's harder to read, we could change it and make it a lighter blue or something. But just as long as it's blue, that's kind of the main thing. Okay. All right. And so it explains to you how you figure out that. All right. So the Pauli exclusion principle says that each electron in an atom must have at least one of these four that are different. Its location in a primary level, its location in a sublevel, its location in an orbital, and its spin. So the Pauli exclusion principle says that no two electrons can have all of these things the same. Let me go back to my illustration on paper here. So within this orbital here, this green, what I label as a green orbital here, I could put two electrons. So that doesn't mean that one electron is in this orbital or one electron is in this antinode and one electron is in this antinode. It means that they are both in here. Electrons don't behave exactly like particles. They're kind of strange. They're both waves and particles all at the same time. And so they exist in both places at the same time, but they have some particle behavior as well. That's kind of weird, but that's, in fact, sometimes physicists call particles that have wave and particle behavior, they call them wavicles, just to give it a name. But so within here, these two electrons exist in the p sublevel. Within, well, the primary level is 2 because we're illustrating here the second primary level. And we have the p sublevel. That's the second of those two things that you have to have different. The third thing is these orbitals. So I've got 3 orbitals within that p sublevel. So this is the third thing in this p orbital. So the other thing that has to be different to have for 2 electrons in this orbital is they have opposite spins. Now that means that one's spinning in this direction and one is spinning in this direction. Okay, that seems kind of strange, but and it may not actually be that they are truly spinning. We just know there's a certain behavior that cancels out the electromagnetic repulsion. Now, you may have heard this in physical science, but when you have 2 particles with the same charge, they want to push apart from each other. They do not want to be together. It's like taking a magnet and putting the 2 north ends of the magnet together. Has everybody done that before? If you have, give me a thumbs up. Let me know you've done that before. Nobody's ever done that before? Oh, I see one person has. So you take 2 north ends of a magnet, they push apart. They won't stick together. But a north and south end of a magnet, they will stick together. Okay? Well, electrons are kind of like that. Well, I'm sorry. Charged particles are kind of like that. Something with a positive charge and something else with a positive charge, they won't go together. They have to fly apart. Well, electrons are all negatively charged. And since electrons can exist in the same space, we said they're both in both these parts of the orbital at the same time. If they followed that rule that we talked about, where things with the same charge fly apart, they shouldn't be able to exist there. The way that we explain that 2, and only 2, particles with the same charge can exist in the same space is we explain it with the term spin. Okay? That also relates to the way that electrons behave when they're going down a wire. So if you plug something into the wall to charge up your computer or charge up your phone, there are electrons flowing through the wire. And if they're flowing in this direction, there's an electromagnetic field set up around that wire. And it goes in the direction of your fingers. If your thumb's pointing toward the direction the electrons are flowing, this field goes in this direction on your right hand. So it's called the right hand rule. Okay. So as long as you have a spin going this way, you go have electrons flowing this way, you got a spin going this way. So electrons going down the wire coming out of the wall, because your wire plugging in has two wires in there. Then you got an opposite spin going the opposite direction. They cancel each other out. And that's the reason you usually have on wires, you got them both the electrons flowing in one direction and flowing in the other direction at the same time, so those fields can cancel out. You don't have a lot of interference with the radio waves and TV and radio and things like that in your home. You have the signal coming to your TV is in a coaxial cable. That means there's a wire down the center where the signal goes in and a braided wire on the outside where the signal goes out, and they cancel each other, and it keeps you from having interference with your TV signal. If you have an antenna for your radio, or even your phone has an antenna, it's just internal, you can't see it anymore. You used to have antennas sticking out of cell phones. But the reason that they work is that electromagnetic waves hit that antenna and induce that direction of electromagnetic spin around the wire that makes up the antenna and pushes the electrons through there. And if it's spinning in this direction, then the electrons have to go this way. And that's the way you get signals out of the air on a radio or Wi-Fi for that matter. Okay? All right, let's go back to our text then and take a look and see where we are. All right, we talked about how the Pauli exclusion principle works. Okay. And now we're going to get to more regions of the periodic table. More regions of the periodic table. Okay. So we've been talking about this S sublevel, and there's an S sublevel in the first primary level below that inside of all of this, and the P sublevel that's made up by these orbital shapes. Okay. But there are other sublevels as well. As you go further down the periodic table, let me put my periodic table up here and show you. So the first level only has, and these atoms are placed on this first row of the periodic table, the hydrogen and helium, because they only have one primary energy level with 2 electrons. So this has 1 electron in the first primary level. This has 2 electrons. The helium has 2 electrons in the first primary level. Then when we get here to lithium, now we're getting into the second level. That's what we're illustrating with this. So lithium has 2 primary energy levels, and everything on this row of the periodic table are elements that in their ground state have just 2 primary energy levels. Lithium and beryllium have only electrons in the S sublevel. So I've got 1 electron in the S sublevel, second primary level for lithium, but the 2 electrons represented by the position of hydrogen and helium in the first primary level, they're still there. So lithium has 3 electrons. Okay, that 3 right there means it has 3 protons and therefore 3 electrons. You've got the 2 electrons in that first primary level that hydrogen and helium had, but now we've added an electron to the second primary level, and that's why it's in the second row. Every time you go down to a new row, it indicates that you're adding more electrons to a new primary energy level. Every time you enter a new row on the periodic table, it means you are adding electrons to a new primary energy level so long as those electrons are in the ground state. That is to say, the lowest possible energy state. So hydrogen and helium have 1 primary energy level. All these elements in here, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon, they all have electrons in both the first primary level and the second primary level. Okay? And so when we get down here, actually when you start in the third row, but you don't actually see it till you get to the fourth row, we're putting electrons into a new kind of sublevel. We're not going to learn about the orbitals and the orbital shapes that exist for these elements. We're going to talk about them, but you don't have to know their shapes. They get more complex. You'll see those in college, okay? But for now, we're only going to deal with the S and P sublevels and their orbitals and their orbital shapes, okay? But these have a D sublevel in them, okay? All these elements here have a D sublevel in them. These elements down here also have an F sublevel, and so do these elements that follow them on the periodic table. Let me see if I can remind you of that, try to make sure we're clear about the F sublevel. So remember when we got to lanthanum, we went from lanthanum to cerium. And this section down here actually belongs in here. If we were to cut this out here and move it over, this would fit right there. We go from 57 lanthanum to 58 cerium, from lutetium 71 to hafnium 72. So this really belongs inset here. And so all these elements right here on these rows, they have an S sublevel, and these all have an F sublevel. Okay, so when we're looking at this text, it's showing you what we call the S, P, D, and F sublevel regions, because it kind of indicates where those are and where we're filling up those. It doesn't mean that you only have electrons in those regions. Remember, a D sublevel region would exist even in, well, and I haven't mentioned this, but would even exist over here beyond this line right here. Okay, so these elements down in the lower part of the P sublevel region also have D sublevel electrons, but this is called the D sublevel region because it's where we're putting electrons and adding more and more electrons into them as we walk our way up through the elements in the periodic table. And then this is the same thing with the F sublevel region. It's called the F sublevel region because we're adding more and more electrons as we go along this row here. All right? Okay. Now this is a bit more complex, but it, to a large degree, kind of shows the same thing. It's just a lot of things piled in there so you can kind of see how they're all interconnected, okay? So what I have, this would be hydrogen and helium here. Let me go back up to this illustration here. When we're talking about this S sublevel region, helium, which is normally on the periodic table over here in the upper right, actually belongs here because helium only has electrons in the S sublevel. So the periodic table and its layout is not perfect. There are some exceptions that you kind of just got to know. And I'm telling you about one of those right now. Helium generally behaves like a noble gas. That's why it's over here in this column with the other noble gases. But when we start to talk about S sublevel regions, it really ought to be put right here. We'll find out later, hydrogen, because it behaves like a nonmetal, really belongs over here when we're talking about nonmetals. But if we're talking about the way that they chemically behave, hydrogen best belongs right here, and helium best belongs right here. So it's kind of difficult to put everything exactly where it belongs, but you just have to kind of know what the exceptions are, okay? So when I give you the outline, the sheet, it'll be 2 sheets with outlines of the periodic table. You need to make sure you label one of your outlines to show where the sublevel regions are located, where the S sublevel region is located, where the P sublevel region is located, where the D sublevel region is located, and where the SF sublevel region is located. And when you write out that illustration, you need to make sure you indicate that helium doesn't belong here, it belongs over here. So you draw an arrow just like I did here. Draw an arrow from here to here and pencil in a box and write helium in here. In fact, if you want to, you can just kind of do a little strike through on this helium over here. Don't scratch it out. Well, I noticed in some people's lab notebook, when you turned in your pre-lab for the saltwater density lab, that some people had scratched out some things. If you make a mistake in your lab logbook, you don't scratch it out. You don't use white out. You don't tear it out. You don't erase it. You draw a single line through the mistake. And I want you to kind of keep that where you see there was helium here in the beginning. So if you want to put an X over it, or you want to put just a single line through helium, you can do that just to show that it doesn't really belong there and you moved it over here. Okay? So this really gets into all the stuff, including those quantum numbers that we talked about. We don't teach really in high school chemistry right now. Not in the, well, really, I don't think any high school chemistry class deals with quantum numbers. You deal with it in college. So that M right there, that's one of the quantum number indications. So that's why those M's are there. That indicates what the spin is, and the P is the L number. There's an L right there. I don't know what else is there. Let's see. Anyway, so this all is kind of all of it kind of piled together. You can see that here we went from the S sublevel over here in these first two columns into that D sublevel. So we went from 4 to 3D, 4S to 3D, and back over here we're up at 4P. So this might help you if you need to go back and look at it when you're having to write for homework your orbital notations and your electron configurations, okay? And here I've just outlined again in a different way where those regions are located. S sublevel region, P sublevel region, D sublevel region, and F sublevel region. So hopefully you've got that, we'll have that straight, and when you write your own illustrations, you'll have that pretty clear. I showed here with a light colored arrow that I moved the helium from over here to over here, okay? All right, the next section is write an orbital notation for all the elements of the periodic table. For us, we are not going to write it for every element on the periodic table. We're only going to do orbital notations through the D sublevel region, through the D sublevels. So for those F sublevel region elements, we're not going to do those down here. We're going to go through all the S, P, and D orbital notations, okay? So let's start with that. So you need your periodic table out, and you need to follow along with me, and I'm going to give you some assignments as we go along. Okay. I'm going to start by showing you how it works, okay? So I'm going to start with hydrogen here. The way you write orbital notation is you write the element symbol. The element symbol is going to be required, okay? And you put a colon after the element symbol. That's a double dot vertically arranged, okay? And then hydrogen is on the first row of the periodic table. And as I talked about earlier, that means it has electrons in that first primary energy level. We are going to show that first primary energy level by putting a 1 kind of below the line here. There's the number 1, okay? And we said that hydrogen is in this S sublevel region here, which indicates that the electrons that I put in here are in the S sublevel. So we're going to put S right here. It's just lowercase letter s. You have to make sure your S is not the same size as the 1. It needs to be a lowercase letter s, okay? Now the orbitals themselves, we're not going to show the shape of the orbitals. We're just going to show an orbital in our way of doing this inventory system as a box, okay? So we have electrons or an electron in the first primary level, which corresponds to the fact that this is on the first row. We have electrons in the S sublevel, which corresponds to the position of hydrogen in this S sublevel region, because electrons are going into that S sublevel. And then we're going to show the first electron. And the way we show that is to try and show an illustration of spin. Remember, we can only get 2 electrons in the same orbital. If I put 2 electrons in this S sublevel and this S orbital, if I put 2 electrons in there, they're going to have opposite spins. That's part of what the Pauli exclusion principle was about. You can't have 2 quantum numbers, 2 sets of quantum numbers exactly the same for 2 different electrons. So electrons have to have spin to put them in the same orbital. So if I put in this S sublevel, well, the one we're talking about right now is this inset part, the lower level here. If I put two electrons as lower level, they're going to have opposite spins. Where we illustrate spins is with an arrow. And the first spin is always going to be an up arrow. And I'm just going to use a half arrow, kind of a button hook or a fish hook or something. Okay, I'm going to show that going like that. It's just faster when you have to do tons and tons of electron symbols. And if we're going to be walking through most of these, you're going to have I don't know, for sure we're going to be doing 57, 60, and then all these over here, another 12. So we're going to be doing 72 orbital notation. So that's a lot of electrons to illustrate. So just to make it faster, we're going to use, instead of doing a full arrow would look like this. And you can do that if you want to. We're going to use that half arrow sort of thing just to kind of speed it up, okay? So that's the orbital notation for hydrogen, okay? That's all there is to it. Now helium, remember, please try to remember, keep in mind, it actually belongs here because it's in the S sublevel region because it only has an S sublevel. It doesn't have any P sublevels, electrons, or D sublevel electrons or F sublevel electrons. So it really, when we're talking about those regions, it belongs here. When we're talking about chemical behavior, hydrogen does belong here and helium does belong here. All right, so we're going to write the element symbol and we're going to use a colon and we're going to have that first primary level. We're going to have that S sublevel and we're going to have the orbital because it only has one orbital. Okay, it's just that first primary level which only has one kind of orbital. We have two electrons and we're going to have to have two different spins to get those two electrons in the same orbital. Well, what shape do you think that second electron is going to have? What kind of image are we going to put there? Anybody? Go ahead, great. Yeah, open your microphone up and tell us. I see you thinking about it. What do you think?
I think 3 left.
Oh, I can't hear you. Maybe I don't have my I don't have my speaker on. Let me make sure I got the speaker on. I'm sorry. That's on me. All right, try again.
I think 3 left.
What do you think? What kind of shape is it going to be in? How are we going to draw that second spin on that electron?
3 left.
Nope, we're going to just go up. I mean, if this is up, I'm going to go down. Okay, that's it. Opposite spins. Okay, so if we have one up and one this way, that's not opposite, is it? Right? It's opposite if one is going up and one is going down. That makes sense? Okay, but you're thinking about it, and that's opening the door to remembering it. Okay, when you're thinking about it yourself and you're attempting to answer the question, and I know I prompted you to do it, but that's how you open the door to figuring this stuff out. Okay, it also helps me because if you have misunderstandings about things, then I can help to ferret out the misunderstandings and replace them with the correct understandings. Okay, all right. So then after we get hydrogen and helium, with helium really belonging here, we're talking about S, P, D, and F sublevel regions, we're going to go to lithium. And that's at a new primary energy level. Now, so this first level still exists. It has 3 electrons. This 3 actually tells you how many protons you have in the nucleus. But for an atom, if it's not an ion is charged, so you have a different number of electrons. But for an atom, you've got an equal number of protons and electrons. Protons are positive and electrons are negative. That's part of what holds this whole atom structure together. But 2 electrons are going to exist in this first primary energy level. So when we write lithium, we're going to start out with exactly the same stuff, 1s and an orbital that's full, just like the electrons that we had in helium. Okay? But then we've got to put an electron in the second primary level in the S sublevel. Okay? So it's going to be 2s. We put this first electron in. Okay? And we're going to have an orbital box. And what will that first electron look like? Carly, what will the first electron look like? Unmute your microphone and tell us what you think. You there, Carly? Just unmute your microphone and tell us what you
I'm
think.
sorry, what did you say?
Yeah. What do you think that first the electron for lithium is going to look like in this orbital rotation arrangement?
I don't know.
Okay. Well, what do we make our first one look like over here?
I don't know.
Well, I got it right here.
1?
It looks, well, that's not a 1 though, is it? Okay. I appreciate you're trying to answer the question, but you gotta pay attention. You got to take notes. Okay, that's an arrow. Okay. All right. So it's going to be an arrow, just like that one. The first one's going to be an up arrow. The first electron you put in an orbital is always going to be up. Okay. It doesn't mean that that's nothing special about it, but that's just traditionally the way it is. It gets into complex stuff that's beyond the scope of this class, and I don't want to try to explain it, okay? But it's just basically going to be, the first one's always up, okay? It just means it has a spin that's going to be opposite from the second one. And that's all there is to writing the orbital rotation for lithium, because it only has one electron in that second primary level, in that s sublevel, in that s orbital, okay? Beryllium then is going to have another electron in that same orbital, okay? So I'll tell you what, why don't you write out what you think the orbital rotation for beryllium might look like, okay? Write out what you think the orbital rotation for beryllium might look like on your paper. Let me give you a minute or two to do that. And if you're really think you got it, maybe you can show it on your camera what you think it looks like. Hold it up to the camera and show us. In a minute, I might require you to do that, so everybody pay attention and do the work. Anybody like to volunteer to show me what they think it might look like? Just to kind of get us off on started here. I don't see anybody volunteering. Okay. So beryllium is Be. We got a colon. We've got 1s, and both the electrons in 1s are there. And then we've got 2s, and lithium had that one electron with an up arrow. And the second electron is going to be a down arrow. Okay? That makes sense? All right, Quaithlin, I'm going to show you the next one and give you a chance to do the one after that. How about that? Quaithlin, you follow me? Up. Quaithlin, give me a thumbs up or something. Let me know you're there. Okay, here we go. So the next element we come to is boron. Now, if you remember when we're talking about the regions of the periodic table, I can show you back on the text here in a second. Pull it up. All right. Boron is over here in the p sublevel region. Okay. So we get the boron. We're going to do all the same stuff. We're just building on it. 1 goes here, 2 electrons. 2s goes here, 2 electrons, and we can only get 2 electrons in an orbital. Okay, so that's those two orbitals are full. When we get over here, we're not in s anymore. We're in p. So this is 2p, and we're going to have 1, 2, 3, 4, 5, 6 electrons. And since those orbitals can only have 2 electrons in them, we need 3 orbitals. And even if you only have 1 electron over here, you got to show all 3 orbitals. Okay? And that first electron is always going to be an up arrow.